Thanks for having me. So I can probably maybe, this is not just as a preface, I'm not going to be going through any Jupyter notebooks, so hope you get your expectations down. However, I will be sharing a bit of details on a use case that my team led while I was at Amgen, and then I can also link to the publication, as I'm sure a number of you might be interested in looking at it in more detail. I was messaging with Bruce directly before, so I think, since most of you guys are MBANs and there's a number of LGOs here, I can tell you a little bit about where I came from and why am I now at League. So I did my undergrad at MIT in biological engineering. After that, I went to a Danaher subsidiary, Beckman Coulter, where I worked in R&D on high-speed biological cell sorters. And I was really excited about statistics, how we characterize our manufacturing, modeling our systems, from a mathematical standpoint, and then that led me obviously to LGO. In LGO, I did my master's in biological engineering with Amgen. And so after LGO, I joined Amgen originally in the process development organization. Most of the LGO theses actually in the past couple of years have been in process development. And it's just a wonderful part of Amgen. And so I started there, and then I actually moved into a sort of a corporate AI initiative at Amgen. And that led me to build up our digital health organization with my boss, Patrick. And then I ended up taking on and building out my own team to do data science and engineering. So when I was at Amgen, I had a team of about ranging between 16 and 18 data scientists and machine learning engineers. And we focused on machine learning across all of Amgen. So early stage R&D, do we think this is a target we could develop a cancer therapeutic for? To understanding biosimilar pricing and predicting what prices we should price our drugs at from a game theory standpoint. But one of the use cases that that I'm going to talk to you about today is essentially what I would characterize as machine learning outcomes research. And this means using machine learning on healthcare data to better understand people's health and therefore then help them improve it. And that actually led me to, I just left Amgen 3 weeks ago to join League as VP Data. League is a digital health startup. They're Series B funded. There's over 300 people, and they historically have focused on selling software as a service to employers to help their employees manage their health benefits. But they're now moving into sort of more of a platform model, a health operating system that has a bunch of software systems that help both healthcare organizations as well as employers build out digital health solutions. So that's what I'm doing. I will likely be recruiting in the near term, so please contact me if you're interested in a role. But now I'm going to talk a little bit about time series forecasting with a slant in healthcare.
I was going to ask. One thing I forgot to mention is Carrie is also one of the esteemed advisory board members for MIT MIMO. So thank you, Carrie, for that.
Thanks, Bruce. Yeah, that's a.
Sorry to interrupt.
I should have included that plug-in. I'm going to skip this slide actually, because I'm guessing you guys already talked about why time series forecasting, especially from a manufacturing and supply chain standpoint. But some other maybe obvious examples, especially for LGOs, are demand forecasting. Demand forecasting is not only important from an inventory management standpoint, but also when you're looking at financial performance for an enterprise, being able to accurately forecast out your demand is non-trivial in terms of what you're reporting to the street. And so actually some of the work I did at Amgen last year in particular was understanding what is the impact of COVID spread and infections on Amgen's potential demand. Because if people aren't going to the doctor because they're scared of COVID, then they're not getting diagnosed for disease, and then they're not getting prescribed for treatment to treat that disease. And so obviously a lot of fluidity, a lot of variability in terms of how COVID has spread, but we really worked closely to last year on understanding that to help inform our demand forecast from that standpoint. So just a side note that LGOs might not typically think of in the context of demand forecasting, it's not just for inventory management, it's also just fundamentally important to your business. And then I mentioned pandemic spread. Actually, a lot of techniques that were published and shared last year were using techniques ranging from RNNs to more typical time series analyses to predict out where we thought what would happen from a COVID-19 pandemic standpoint. And then the last example, which is the one I'm going to focus on for this talk, is predicting patients' risk. And this one is weird. Like, you wouldn't think to apply techniques from time series analyses to predicting patients' risk, but I will show you an example where we did this very thing. I'm going to not go into detail here on the different methodologies. It sounds like you just, had a good demo on LSTMs and using that in TensorFlow. There's a number of different methods that are available. When I was at Amgen, we definitely experimented with AWS Forecast, as well as, more mechanistic type models to do time series predictions. It really depends on the use case. A non-trivial element of deciding like what approach to use for time series forecasting is kind of like who is consuming the results of what you're generating and how important is interpretability, and as well as like usability. So like the example I gave last year in terms of understanding Amgen's demand forecast as a function of COVID-19 spread, like we could have gone with a very sophisticated approach. We went with a very, frankly, trivial approach. And the reason was that we needed a simple way to be able to engage with our commercial, traditional forecasters quickly so that we could report, analyses that could be used by our executive team in support of earnings calls. So saying, oh, hey, it's this RNN that we came up with is like not helpful in that context when it needs to be fast moving, highly interpretable, and frankly, like all models are wrong, some are useful. Like I think that is something that we really need to take to heart, especially those of us in data science. But in other cases where the use case really merits a deep learning approach, they could be obviously extremely powerful. So the example I'm going to talk about is on my team's work to develop a deep learning model to predict someone's risk of a osteoporotic fracture in the next 2 years. So the question is like, why is this important? Little known, or maybe you do know, or you have a relative that has had an osteoporotic fracture, they result in a really significant burden from a healthcare cost and just like from an independence cost. So when somebody has a fracture, it can really lead to a severe decline in their health because they're not mobile, which has a lot of downstream effects. They lose independence. They're not able to go do stuff by themselves. They're in a wheelchair. And then they also lead to costs in terms of caregivers that need to take care of them. And over the past 20 years, because of declining Medicare reimbursement in bone density scanners, it's actually interesting. It's like a downstream effect of a totally like a healthcare policy. Because people aren't getting their bones checked for their bone density, they're not even aware they're at risk of an osteoporotic fracture. And so what has now happened is people get treated for fractures after they've already had one, instead of identifying when they could have a fracture based on their bone density and then treating them. And the existing risk tools are not frequently utilized, and they operate on a 10-year time frame. So the most frequently used tool, when I say tool, it's like a literal calculator. The calculator that's most frequently used by clinicians is called FRAX. Basically, you put in like your name, your age, and a bunch of self-reported information, including like how many drinks you have a week. So now I know personally how like inaccurate that information can be, and also how unusable it is, because I did it with my dad, and he was like, "Oh yeah, like I don't drink that much," and like, what do they mean by smoke? Like he has a medical marijuana card for Massachusetts, so like he thinks, oh no, that doesn't count. I don't need to put that in there. People aren't truthful when you ask them to report information on their health. And then also operating on a 10-year time frame, it's not actionable. Like if you say, oh, my risk of having a hip fracture in the next 10 years is 10%, I'm like, oh, only 10%? I'm good. I don't have to do anything. And so being able to understand people's risk in the next 2 years is really important. And also, from an Amgen standpoint, Amgen has 2 bone acting agents that Amgen manufactures that are used to treat this, so that people don't have a fracture, and actually helps their bone cells grow back. And so, the work that my team set out to do was to see if we could use deep learning to be able to predict someone's risk of a fracture in the next 2 years. And so it's really funny because this all started with an electronic health record data set that my team had in like an S3 bucket. And we were like, what should we do with this? And I had a couple new data scientists on the team, and we knew that prediction of fracture, if we could shrink it to 2 years, was really important. We were putting out, clinical study proposals for external groups to study. And I was like, okay, like have at it. Like, let's see what we could do. And so my team started looking at it, 2 computer scientists, one from Princeton, the other from USC, not people with healthcare background. And they start looking through the electronic health record data. And they're looking at the diagnosis codes. And so, and there's probably like very few people on this call that have worked with healthcare data, but basically what it looks like is this transactional data. And every time you go to a doctor and you have an insurance claim or a visit that's associated with it, the doctor is putting in what diagnosis that they think you have, and that gets coded to a specific billing code that defines like how much money they get for the visit, and also defines in your electronic medical record what you were diagnosed with. And so those codes, those transactional codes, are basically strings that are defined by International Classification of Diagnoses that tell you like what you have. And so like Z100 here is like you got a regular checkup, I10 is hypertension, M81 is osteoporosis, and then M80 is a fracture. And so you're having all this transactional history for patients in an EMR data set for a given patient ID. So you have tons of transactional information over time of patients receiving different diagnoses. So my team's idea was, can we use techniques that are from natural language processing and predict if the next word in a sentence would be fracture? So essentially, the example I'm showing here is if you have a sentence and it's I want to go to, we're predicting the target label. Is it going to be New York, or is it going to be some other word from our vocabulary? In this example, you're stringing together, sequences of strings that are different diagnosis codes, and we're making a prediction on whether you're going to have a fracture in the future. And my team had been inspired by some conferences that they went to. We saw examples from the literature where this kind of technique was being used for language and also applied for electronic health record coding systems. So we thought, hey, we'll give it a shot. Let's see what we could do. And so the architecture that the team that we took on is the following. So essentially we feed in a sequential input, which is the string of the list of strings of the diagnosis codes that the patient has had. And the data, I should go back for a second, like the data set that the team worked with was, I think, over 2 million patients over the past 10 years. And then I think it's all in the papers. I think we did like a 70-30 train test split. And what we first did was we fed it into an ICD-to-VEC embedding layer. And so the purpose of this is, in natural language, you can just straight up use a word-to-VEC model that's pre-trained. But because we're using sequences of diagnosis codes, we want to really develop the semantic understanding of like, how is hypertension related to diabetes? Like, how is this fracture related to this? Instead of having to do a massive like one-hot encoding business rule structure to say, do they have this list of codes? Did it occur during this time? We're just feeding lists of strings. And so to be able to compress the data set, given that there's like thousands of diagnosis codes, we used ICD-to-VEC, an embedding layer. I'm showing on the bottom left a visualization using UMAP, uniform manifold approximation projection, to actually visualize like how reasonable were the embeddings that we generated from our data set in terms of the codes. And what's really cool, and like frankly we didn't know that this would happen, which is wild, is that we see that the codes that are associated with different parts of the body actually cluster together. So essentially what that's showing to us is that our layer is actually learning that diagnoses that are in a given type of the body are related to each other. And this was all converted, like this is all purely one-hot encoded when we feed it into the embedding layer. So it's not like we're looking at the string names and identifying similarity. We're getting the embedding based on the similarity of the context of which they're occurring in the sequence. And so this isn't like incredibly novel. There are papers that are showing that this methodology can be used on sequences of diagnoses. What we then did is we fed it into a layer of LSTMs to then predict actually someone's risk of having a fracture in the next 2 years using their age, gender, and then we use the total number of diagnoses as an additional data point to input to kind of like give a sense of the severity of the condition. So if someone's not sick, they may have a lot of diagnosis codes versus someone is not, if they're not sick, they may have very few diagnosis codes because they don't need to go to the doctor very much. If someone's very sick, they may have an enormous number of diagnosis codes. And then on the lower right-hand side, you can also see another UMAP embedding plot. UMAP, by the way, is like an alternative to TSNE for visualizing embeddings. So like most of the historical Word2Vec papers that you might read show TSNE to visualize the embeddings. TSNE has a lot of not great elements to it. You have to kind of fiddle with the different variables that are present to get the visualizations that you're looking for to see kind of how the embedding is working, the TSNE embedding is working. What we liked about UMAP is we just see like a lot clearer distinction in the clusters that are identified. And then UMAP actually, like side note, I'm like a big UMAP fan. UMAP is like highly performant, and it also has gotten a lot of popularity in the biology field in the past couple of years because it performs extremely well on extremely high dimensional data sets. So just like FYI, the docs are not great. And so if you're trying to implement UMAP, there's like weird nuances that you have to sadly like make your way through Stack Overflow on. But in general, if you have like pretty straightforward use cases, UMAP is, I think, really a really cool methodology. And so, what was neat is then when we apply this technique to predict someone's fracture, we get an extremely high area under the ROC curve. We also applied another technique we called it patient-to-vec, which is kind of like doc-to-vec. So we do kind of document level embedding. So instead of on a sequence of codes learning the semantic relationship between the different codes, we're trying to learn like similarities of patients to each other and then classifying them. We didn't see, like there's some metrics there, you'll see it's slightly worse in performance, and actually the interpretability is a lot more difficult versus if you use like an embedding based off the sequences of diagnosis codes, it's a lot easier to understand because you can actually look and say, oh, okay, I see the embeddings, like, diagnoses related to hypertension or related to other cardiovascular conditions. So I have some confidence that like my model isn't totally wrong. We also compared our model to a number of baselines using just age and gender. Age and gender, frankly, is usually like highly performant just because fractures are more common in postmenopausal women due to declines in estrogen. So there's like biological reasons why they're more prevalent. So even just using age and gender, you can generate like a not terrible performance, but we definitely do see a marked improvement in the model over those baselines, as well as it's not an apples to apples comparison, but we did a thorough literature review on other models that are used to do fracture prediction in particular, and our method far surpassed them. And in fact, after this publication, we even submitted a pre-submission inquiry to the FDA and received a lot of really good feedback from the FDA at the end of last year before I left. Also, regarding the FDA and like questions on regulations on AI and machine learning solutions in healthcare, the FDA is very much with the times. And if any of you are interested in machine learning solutions in healthcare and you think that FDA is your excuse, or you think it's going to be too high a bar, they are extremely forward thinking and they have very knowledgeable people there. I'd encourage you, if you're interested in like making your own company in like the AI machine learning in the healthcare space, read some of the regulations that the FDA has put out recently. They're very much with the times. And then I just wanted to say, I just think this is cool. Like, and also I'm not into video games, but a lot of people are obviously, but I just think this is so wild that this technique can be used in this space. So this concept of using like the implementation of Word2Vec for sequences of actions or sequences of codes has also been shown to be able to characterize video game player behavior. So if you think of the actions of a video game player over time as like a different action that's taken among a vocabulary of possible actions that they could take, here they're showing an embedding of these actual sort of Word2Vec, action2Vec implementation for, I guess, StarCraft players. And this was presented at ICML in 2019. So I just think it's really interesting and a cool opportunity to apply it to other, manufacturing use cases potentially, or even, predicting user moves in a like manufacturing setting, like in terms of, technician moves in a manufacturing setting, for example. And so and I can certainly kind of go back if there's questions on detail part in here. I went kind of fast because I like to talk about it so much. So I think the takeaway for me from this experience, and I'd like to share here, is that like machine learning approaches from different domains can be repurposed for a lot of different tasks. And I think that that's the value. Frankly, that's like what I love about MIT so much, is that you have such a multidisciplinary perspective. Like methods from one field can be repurposed to another field. And so like we used LSTM to predict fracture. My team last year, we used dynamic time warping, which is like typically used for sequence alignment and genomics, to figure out what counties in the US were more similar from a COVID pandemic standpoint. So like a lot of these techniques are really not like industry specific, and are much more like use case specific. And so I'd encourage you, especially while you're at MIT, to kind of interact with as many people from different parts of the institute as possible, because that's really where like truly creative, cool solutions come from. The other sort of advice or takeaway I would have on time series problems, which we didn't take on the fracture one, like we were very like, let's just give it a shot and see what we can do with this data. We probably should have started with a simpler model first. We ended up going simpler later just to see if we truly had an increase in performance. We were able to do that because it was like a research project, and it turned out to be like a lot more exciting than we ever expected. But typically I would say like go simple first, see if a very simple time series model is effective. And then, you can explore more complex approaches. I also think it's really important to like understand your data and not just like at surface, at face value. This is so important when you're dealing with real life data, like especially for the MBANs, you may be less familiar with like real life data. A lot of real life data is like a total nightmare to work with, and you have to get a lot of context in terms of where it's generated, people that are going to work with the data, people that are consuming your results. And so I think it's like really important to take the time to understand it. And so like in healthcare in particular, diagnosis codes are generated because someone's looking to get paid for a visit that's made. And that can influence what code they're choosing for the reason, because there's different reimbursement levels for the same diagnosis. So like you really need to think through like who's generating the data, what are their sort of potential biases, and obviously like bias in AI is definitely a big topic right now. And then lastly, I would say that, like explore methods and techniques from a variety of different industries or applications. Like you would never expect that, like, for example, autocomplete for Smart Compose in Gmail, that same approach could be used for healthcare data, but what we saw was you can, and it's actually better than what the state of the art was. So I have some time for questions. I don't know if you guys are all like done for the day because it's the end of the day, but I can take some questions.